All right, the second half of this section of 8.1 is dedicated to the surface area. So we talked about arc length first, and that makes sense because if we have a curve, it should have some one-dimensional measure, which is its length. In this case, we call arc length, just to emphasize the fact that it's not the straight line distance from start to finish along the curve, but rather it is the true distance that the curve so it's the true distance if you were to walk that path or travel on that path. So surface area is a little bit different here because we have, if we just talk about what's the surface area of F, that doesn't make a lot of sense because F is something one-dimensional. The curve lives in two dimensions, but the curve itself is a one-dimensional thing, so how can we talk about surface area? Well, here the little caveat is, here we are assuming that we first graph the function f, so we get this one-dimensional curve in the xy plane, and then we rotate that curve about the x-axis, and that will draw out or create a solid or a volume, and that solid has a surface area. So this theorem, theorem 2, is for calculating the surface area of the solid that is the result of rotating our function about the x-axis. You do not have to be completely familiar or reproduce the derivation of this. I have it listed here, but it is very much similar to what we did with arc length. We essentially take our solid, our volume of revolution, we split it up, we partition it into finitely many, arbitrarily small little sections. And if we approximate, just like we did with the arc length, from between two adjacent points, we just connect them with a straight line, then the volume of revolution for that little section isn't this smoothly transitioning curved solid, but rather it's sort of this, it's a portion of a cone, kind of. You can think of a full cone and then just kind of truncating it, so chopping it off here and here, and that little part that sort of looks like a trapezoid that's been rotated, that is called a frustum of a cone, which is a strange word. So ultimately what we do is we break it up into these arbitrarily small frustums of cones, and you find the surface area of that. Add up all of the little chunks to find the total surface area, and then we've essentially built a Riemann sum type idea, and we will, again, very similar common story throughout Calc 2. We'll take a limit, and this will give us the definite integral right here. So the important thing for us to know is that the surface area formula contains that same square root quantity that's present in the arc length integral, but then we also get this 2 pi, the function. Okay? 2 pi the function. So these are going to be two new things. So let's put this into practice and take a look at example 3. Determine the arc length of this function 1/12 x cubed plus x to the negative 1 on the interval 1 to 3. All right, we'll start by writing down our function, taking a derivative. So 3/12 is 1/4 x squared, and then if we do the derivative, this would be minus x to the negative 2. And then we want to square this, which does mean we're going to have to, FOIL this out, multiply it out. So this would become 1/16 x to the 4th. The middle term is these two terms multiplied together times 2. So we got a positive, a negative, times a positive 2, so that's negative. And we would have 1/4 times 1 times 2, so this is negative 1/4. And when we multiply these two x terms together, we get x to the 0th, which of course is just 1. And then the last term, of course, is squared, so this would become positive x to the negative 4. Okay, so let's erase this x to the 0 because we don't need that, and put this right here. All right, we're going to add 1 now to this. So if we add 1, we've got these two new like terms that emerge. And I just realized I don't think I multiplied this term by 2. Right, we should have this term times 2. So this 1/4 should not remain a 1/4. It should become a 1/2. So let's just quickly change that. There we go. So now when we add these two together, there are two like terms. We should have a 16th x to the 4th, positive 1/2 this time, plus x to the negative 1/4. Okay. Believe it or not, this actually is a perfect square. So let's just test this, or verify. I believe, or I'm claiming, that this is the result of a perfect square trinomial, which I believe is 1/4 x squared and positive x to the negative 2. Let's try that. So if we square this out, just to verify that we do indeed get this back, multiply the first term by itself. So this is 1/16 x to the 4th. So far, so good. Our cross terms, again, are the result of multiplying these two and then multiplying by 2. So the x's will cancel, and then we'll be left over with 1/4 times 2, which is 1/2. So 2 out of 3. So far, so good. Lastly, we'll multiply the x to the negative 2 by itself to get x to the negative 4, which does indeed match what we have. So this is a very strange, seemingly unfamiliar, but also quite familiar perfect square trinomial. All right, so I'm just going to go ahead and say that's right there. So we have the inside of the square root figured out, so that's good. So I believe we're ready to continue here. So our surface area should be 2 pi, the integral from 1 to 3. Our function, so we are going to have our 1/12 x to the 3 plus 1 over x, all right, times our square root of our perfect square, dx. All right. So we can take our square root of our perfect square, and then we'll have these two terms that we need to FOIL out, or factor out. Okay, so if we do some distribution here, we should have 1/12 times 1/4 is 1/48 x to the 5th plus 1/12 x, if we do this term times this term, plus we're going to have this term times this term, so the inner term, so to speak. This would be 1/4 x plus x to the negative 3. All right. So continuing up here, the area would be 2 pi. The integral, I'll collect like terms if there are any. So we've got a 1/48 x to the 5th. I'll write this in descending order. We've got 2 copies of x, so this would be 1/2 plus 1/4, so 3/4 x. Plus x to the negative 3 dx. And we can integrate that. So integrating this, we should have 1 over 48 times 6, x to the 6th, plus 3/8 x squared, minus, well, our new exponent is negative 2, so we're dividing by negative 2, so this would be minus 1/2. between 1 and 3. So 2 pi times the quantity 3 to the 6th power over 48 times 6 plus 3 times 3 squared over 8 minus this negative 2 exponent means we're going to have it squared in the bottom, so 1 over 2 times 3 squared. Minus everything with a 1 plugged in. So minus 1 over 48 times 6 minus 3/8 minus a minus, so plus a half. So having paused for a moment and writing out these fractions, getting a common denominator, and writing it all nice and compactly, the surface area is 215 pi over 18. And as I was going and doing this arithmetic, I did notice that the question actually asked us for the arc length, not for the surface area, which is fine because we've done enough arc length problems. So let's just cross this out and say surface area. Much of the problem is the same though if we do surface area, or excuse me, if we had done arc length, because we still would have to figure out all of this, which is arguably the hardest part of the problem, because not everyone notices that this is a perfect square trinomial. But once you get this, the only difference here is we wouldn't have this 2 pi or the function repeated. So our integral would just be from 1 to 3 of this quantity. And the integration there is just as straightforward as it was here. And the numbers plugging in, equally as nice, equally as ugly. But yeah, that's it.